The goals of this lab are to analyze and predict the behavior of circuits with resistors in parallel and series, examine the behavior of ohmic resistors and capacitors using a simulation tool, measure experimental values of current and potential difference with multimeters, and compare experimental values to calculate values. Key concepts that we used in this lab were the node rule, the loop rule, the rule of resistance in parallel and in series, and capacitance. The results of our lab were in our series circuit, the delta V, or our potential difference, was 0 volts. In our RC circuit, the experimental RC came out to be 5.99 seconds, where the calculated RC was 6. In our series circuit, we're going to be using the node rule as stated previously, and here's our circuit. It has 2 batteries, 2 ammeters, 2 resistors of different resistance. Total resistance, because it's in series, is 147 ohms. We use that to find our current, voltage divided by resistance. And then if we replace 1 ammeter with a voltmeter, we have a voltage of 3.0 volts, but our current drops to 0 amps because it's an open circuit with no current and the potential difference is constant. So we closed the circuit from the last part with a wire, measured the potential difference between the various points on the diagram. Here are the potential differences in the measured points. As you can see on the far right are the points. So A to B 3, B to C 0, C to D negative 9.6 volts, D to E 0, E to F negative 2.04, and F to G, G to H, H to A is all 0. And we can see that the round trip potential difference is equal to 0 as predicted by our loop rule. The potential difference across the loops are shown by this graph. The reading on the ammeter does not change due to the voltmeter since the resistance is very high, which means that the current is not passing through the voltmeter, leaving the overall current the same. There is an increase in current from 0.2 amps to 0.6 amps as an effect of the current encountering less resistance being split between the 100 ohm resistor and the ammeter, which can be modeled by the formula I equals V divided by R, showing that when resistance decreases, current increases. Here we are using Ohm's law and the experimental data to determine the experimental values of the resistors for the 47 ohm resistor, 100 ohm resistor, ammeter, and wires. You can see that for the resistors they become slightly increased in resistance, and the ammeter and wire has a resistance of 0. For our RC circuit, our system includes a 10 ohm light bulb, 9 volt battery, and a 200 millifarad capacitor. Observations of when our system ran is the light bulb starts off glowing very brightly, then slowly grows dimmer and dimmer over time while the battery is still connected, meaning that current is dissipating. Once the battery is disconnected, the light bulb lights up again and slowly dims again, showing a dissipation of current once more. Here is the time it takes to discharge with the 10 ohm bulb versus a 20 ohm. You can see the data collected from our previous experiment, and we're going to plot it onto a graph using that equation seen in the top right. It yields a linear slope, a linear line of data, and we're going to use that to calculate RC. So our experimental RC ended up being 5.99 seconds, and our calculated RC was exactly 6 seconds. Question 1. An ammeter in real life has a very small non-zero resistance, in addition to the very small non-zero resistance of the wires. This would result in a slightly decreased current being read by the ammeter. What if question number 2? The ideal model would predict the capacitor reaches full charge almost instantaneously, which would not happen in real life because the wires and the capacitor itself have a non-zero resistance which would increase the required time needed for the current to travel.